All right, let's do the second part of this RT level design. The only reason I'm doing this is we have already done a multiplication, a multiplier. And I showed you a very simple algorithm. It's a bad algorithm. If you're multiplying two 64-bit numbers, it may take forever, many clock cycles for you to finish it. Okay, so nobody does multiplication like that. The reason I'm doing this is to show you other algorithms, other possibilities for performing multiplication, which we are not going to be covering in this course, but then just so that you don't leave the course with learning a bad multiplication algorithm. I want you to understand there are also good multiplication algorithms. All right, let's start with this. This is a 8-bit multiplication, A and B. If I were to do this using the previous method, I have to add B to P, add B to P a number of times. Okay, what is A? A is 1, 2, 4, 16, 32, 64, 128, 148. Okay, that means it would take 48 clock cycles. Okay, what does A consist of? A is 1, 0, 0, 1, 0, 1, 0, 0. Position 0, position 1, position 2, 3, 4, 5, 6, 7. Okay. There is a 1 in position 2, there is a 1 in position 4, and there is a 1 in position 7. 1 in position 2 multiplies the B by 4. 1 in position 4 multiplies B by 16. 1 in position 7 multiplies B by 128. Okay? What it means is 1 in position 4 requires B to be added to P 16 number of times. So you have, for the sake of this one, you have to clock 1, clock 2, clock 16, so that you take care of the 1 in this position. For the 1 in the 7th position, you have to do 128 clock cycles. But then, let me take the simpler one also. The 1 in position 2, you have to do 4 times B added to P. Let's, for the sake of argument, just say that B is this 0, 0, 1, 0, 0, 1, 0. No, I want a small one, small b. This, okay? Let's say this is my b. And let's say I have found the position. This is A, by the way. I have found that in position 2 there is a 1, and therefore this B has to be added to P. This B has to be added to P 4 times because of that one that I'm pointing to. Because of this one that I'm pointing to. Now, there are other ones that other B's have to be added to P, but this one is responsible for adding B to P 4 times. What if instead of adding B to P 4 times, I take position 2, shift B to the left 2 positions, 2 places, let's say places. Position 2 of the one that I'm dealing with, position 2 of the one that I'm dealing with, okay? I shift my B 2 places, the same number, 2 places to the left. That becomes B times 4. Look, if this is 5, this is 1, 2, 4, 8, 16, that's 20. So instead of, in order to deal with, let me do highlighter, let me do orange or green. Instead of dealing with this one of A by taking the original B, adding it to P 4 times, I say, why not take the B shifted to the left 2 places, that's log 2 of 4, or the position of that 1. Let's shift B to the left 2 places, and then take that shifted B, not really shifted, turn it around the wires, and then add that to P. And then the same thing with this last one here. This last one here. This last one is on position 7 of A. Okay, which means that I have to add B to P 128 times. What if instead of doing this, I make a shifted B 7 places to the left, that means B times 128, and only do one adding with the P. But that requires 8 zeros on the left-hand side of B, so that I can shift left. What I'm doing here is I am adding and shifting. This multiplication procedure is called add and shift, or shift and add. Okay? And then what happens is, I don't, for this number here, 148 is A, I'm not going to take 148 clock cycles like the previous one. Instead, what I'm going to be doing is I will be taking only 8 clock cycles for the entire multiplication. And how do I do this? I look at bits of A. I look at the first bit of A. Is it 0 or is it 1? It's 0. So let's not add, just shift. Okay? And this shifting is really not shifting, it's shifting for preparing for the next one. So I have already formed a shifted B 1 place. Then I look at the next one. Again 0. So I'm not going to add, but then I form a shifted B. Sorry, this first one is 0 place. Okay? The next one, 1 place. The next one, 2 places. But then that's 1. So I say, 1 is in second place. I have already prepared my B shifted 2 places to the left. So let's take to the left. Let's take this shifted P to the left. Because there is a 1, let's add it to P. Okay? This is all good. There are 2 little exceptions. Not exceptions, but it's really 2 little things that are different than what I just said. I said, let's go from right left of A, right bit of A, and then bit by bit go to the left. What if instead of doing this, I sit in one place and let A shift to the right one place, and therefore I will be looking at the rightmost bit of A all the time. And as I'm looking, A is being shifted to the right, and therefore I'll be looking at the 0, the 1, the 2, and then the first clock, I'll be looking at the 0 on the right hand side. The second clock, I'll be looking at the 1 or the 0, and the third clock, I'll be looking at this position. Okay, so I go according to clock, and in each clock, I look to see if there is a 1 or there is a 0. If there is a 1, the shifting has to be done according to that. That's one thing. So I don't go to the left, I let A come to the right. That's one thing. The other thing is, I said let B get shifted to the left, here, get shifted to the left and get added to P. Partial product, get added to P. Instead of that, see, this is P, this is B. I'm adding B to the, shifting B to the left, adding it with P. What if, when I write my P, I write my P one place to the right with each clock? And therefore, when B is added to it, I will not be shifting B to the left relative to P, which has been written one place to the right. B is one place to its left. And therefore, both A is shifted to the right, and also the data that is being written into the P register is being shifted to the right. Okay? And therefore, I don't do any left shifting, I do right shifting. All in all, this is the multiplier I'm designing. This is again, I'm doing 4 bits to be consistent with the other one. But then this is much better, because if I have a 64-bit A, 64-bit B, this only takes 64 clock cycles for the entire multiplication. Not 2 to 64, which is 65,000 something. Okay? This is the data path, and the detail I go through is as much as I have already discussed. Okay? I have A register. A register sends A0 to the controller. Tell the controller my rightmost bit is 0. But then A register is a shift register, so that each time it shifts, it will be displaying one of its bits to the controller, saying, okay, A0 is really not A0, is now after 3 shifts is A3, for example. Okay? Gives it to the controller. The controller will be thus looking at these bits, this bit, the orange bit, the green bit, one at each clock. When it reaches the green bit, it knows it has expired all the bits of A, and all the shifting and adding that need to be done are done, and then the whole job, the whole task is done. So I need a shift register. I have an A bus that comes in that takes 4 bits and puts the input into the A register. I have B bus that comes in, puts the B bus into the B register. And then I have a P register here. Why is my P register 4 bits, even though I said the result is 8 bits? Look, this is another key thing. What happens is this. As I'm shifting A to the right, remember I said that the result of add comes in, gets written into the P register, shifted one place to the right. So that the next adding will be P added to B with B relative to P one place to the left. So P has to be written into the P register or this temporary product register one place to the right. What happens to that rightmost bit of it? But remember that A is emptying out each time I'm shifting it one place to the right. The back of it is getting empty. And P each time is getting shifted one place to the right. So I just take that one place to the right, which becomes the output, the final output, which becomes the first time is this, the second time is this. The first 8 bits, as they are ready, they move into the back of the A register that is getting empty by A shifted out one place to the right. After 8 clocks, A is out, completely out. The room on the left-hand side of it is filled by the new P's that are coming in. And therefore, you are seeing a serial bit from the add bus gets shifted into the serial in of the A register. This is serial in. And this is the P register. The P register gets added with the B register, but then I don't necessarily add the B register with the P register all the time. Sometimes I add 0, because if my rightmost bit of A is 0, when my rightmost bit of A is 0, like this case here, okay, like this case here, which I put in a very busy diagram, I should put an arrow, this one here, okay. If this is 0, then I don't want to add B. I want to add 0. And therefore, I put these AND gates here so that they select 0 and add 0 to shifted P, shifted right P. Depending on the bit of A, this thing, that goes to the controller decides if it's 0, it says B 0. Has to be added with the shifted P. If this is 1, it says B. So B select becomes 1, has to be added with the shifted P. The shifted B and P get added. They come through this bus here. The least significant bit of this bus goes shifted into A. That's the bit that replaces eventually all of A. And then the rest of the bits go into the P register. That becomes the shifted P. The shifted right P, which relative to B, when it gets the next time that it gets added, relative to that, B is to its left. That means B is multiplied by 2. All right. So I did explain the whole thing, and I don't expect you to understand all the details, but I do expect you to appreciate the algorithm that is very different from the previous one, and how the two algorithms are different in performance, in number of clocks. Hardware-wise, not that different. Okay? Initially, I wait for start. I issue ready, and then I wait for start becomes 1. Ready means ready. Okay, like the done in the previous one, and then start becomes 1. Start becomes 1. I'm initializing, and then I load A and B up to this thing. Is at this point everything is the same, and then I go into 8 shift states. The shift states, shift 1 through shift 4. 8, not 8, 4. Sorry, I'm still thinking of 8-bit multiplication. 4 shift states. In each state, I shift A so that I make it ready for the next bit to be sent to me to the controller, which I'll be observing, okay, which is A0. Okay. and then load P. So as I'm shifting, I'm loading the data into the P register. Also, depending on the bit of A, 0 or 1, I'm issuing the B select. The B select means am I selecting B or I'm selecting 0 to be added with that shifted P. Okay. This, after these three states, only 4 clock cycles. For the 64-bit multiplication, instead of 4 clock cycles, you take 64 clock cycles for the entire multiplication. If it gets to that, you don't put 64 states like this. You put a counter that counts 64. Okay? So that's called the shift and add multiplier. Then there are unsigned, this is an unsigned multiplier. There are signed multiplications based on the Booth algorithm. Okay, all of these you will be seeing in more advanced digital circuit courses. Okay, here our purpose was only to show you flow of RTL design. What is RTL? Okay, there is a lot more to RTL than what we have done, and there's a whole course on that, and there's still more to RTL than even 1 or 2 courses. We did a multiplier with a simple algorithm. We did shift and add. I didn't want to go through the very long description of it. I didn't want to go through very details of the algorithm, but that's good enough. And best of luck in your exams and everything.